All right, I'd like to welcome everyone to another installment of our Sustainable Energy Seminar from the Wisconsin Energy Institute. Thanks for those who are repeat attendees, and for those of you, this is your first time, my name is Scott Williams. I'm the Education Manager at the Wisconsin Energy Institute and the host of the Sustainable Energy Seminar. This seminar is held every other week in the fall and the spring semesters to highlight cutting-edge research from across UW-Madison and beyond, and to showcase how different disciplines understand energy challenges and develop solutions. So throughout the series, we hear from experts in science and engineering, as well as social sciences and humanities, to learn about the ways in which they view sustainable energy challenges and solutions. The seminar is open to the public, and it's also a course for students in the undergraduate Engineering for Energy Sustainability certificate, as well as the Master's in Sustainable Systems Engineering program. And this seminar is offered online only through Zoom webinar. And if you've registered today, your registration to this webinar gives you access to all 7 webinars this semester. Live captioning is available for those who'd like to use that feature. You can click the Show Captions button on the bottom of the screen to toggle that feature. And then if you have a question for our presenter, please use the Q&A. If there's a clarifying question, I can interrupt if there's a good stopping time to ask a question to our presenter. Otherwise, we'll have plenty of time at the end of the presentation to do Q&A as well. So with that, I'll introduce today's speaker. Professor Bernie Lesieutre is from the Electrical and Computer Engineering Department here at UW-Madison. His research, teaching, and professional interests all involve electric energy systems and energy analysis and policy. And his research activities involve the development of tools to advance the design of reliable electric power systems, as well as energy policies to support system reliability. He has published numerous reports in support of activities at the U.S. Department of Energy, as well as the Federal Energy Regulatory Commission, and he was a member of the team that helped investigate the August 2003 Northeast blackout. So today he'll be talking about efforts to monitor and maintain grid stability. So welcome, Professor Lesieutre.
Thanks, Scott. And Scott, please alert me if you see any questions. And everyone in the audience, feel free to ask questions as we go along. That's fine. So today I want to talk a little bit about grid stability, and I'm hopefully going to present a perspective that you don't consider every day when we discuss these topics about sustainability and the like. So this plot here on this front page is one of my favorite plots of all time, because it's a real plot from a power system, and it shows a dynamic instability. The red line here shows an oscillation that's just growing and growing and growing and growing over time. And it's like a textbook example of something that we would see. It is probably in a textbook somewhere at this point. Beautiful, beautiful plot, and it's real life. And it's taking the power along the California-Oregon intertie. So the power flowing between California and Oregon. And you can see when this goes unstable, there's hundreds of megawatts in these swings. So it's an enormous amount of power flowing back and forth before the system crumbles. So this is an old plot. It's older than pretty much everyone on this call except me, I suspect. It's from 1995. But it's a beautiful plot showing instability. And this is the type of thing we worry about when we monitor the grid. And I'm going to tie that to our worries with some of the sustainable technologies. Okay. There. Okay, so I'm going to back up and talk about power systems a bit, and some of the control systems that we worry about. So there's a bunch of different timescales, a lot of different timescales where we make decisions about power systems. On the year timescales, over years, we'll talk about siting and construction of facilities. So building a power plant doesn't generally happen in a month. This is a year long. Getting approval, deciding you need it, and then actually building it takes years. Same with transmission, just doing all the planning for it, getting permission to build it, and then actually doing the construction takes years. So that's pretty far out when we do capital investments in the facilities. In the mid-range, we make decisions over months out to a year that do planning for the upcoming season. So seasonal planning is the type of thing we do. So we have transmission lines crisscrossing the country, and we have to determine what the limits of operating limits are for those transmission lines for the next season. What limit should we place on how much power that can go through them and the like? And those are decided on a seasonal basis, but they impact real-time operation of the power grid, because once they're set, we use that in all our decision-making on a fast time scale. There is one line in the country where there is the power flow limits are decided daily, but there's only one that I know of we do that, and that's the Pacific DC intertie, which is a very large transmission line in Western United States. But the rest we do on a seasonal basis. Then we get down to the days and minutes schedule, and this is where we operate electricity markets and the like. And those are done on that time scale. They do involve probably a lot of the decisions are made by computers, but could involve people, deciding on what to offer into the market and just what decisions are made on the electricity and the related ancillary services market. Again, probably with a lot of computer assistance. But at the very fastest time scale, on the order of seconds, then we're operating in a regime where it's all automatic controls. There's signals that are being monitored and actions that are being taken on a second-by-second basis. And that's all automated. We aren't doing that by anybody doing personal intervention. And that's the time scale I want to mostly focus on today, but I'll have some more general comments on that as well. So this is where I live, is on a fast time scale. And I'd like you to think about it today too. So I appreciate the opportunity to talk about this. The electric power industry, let's back up to where we are and talk about this in terms of renewables and sustainable operation. This is data from EIA from 2023. So sorry it's delayed, but their data is always delayed by a year. In fact, I'm just completely happy they still have data. So from 2023, came out in 2024, but it'll be later in 2025 before we have 2024 data. So this shows that on the left here, natural gas is about 40% of our electricity supply, coal another 16%, and roughly 20% nuclear, roughly 20% renewables. And then on the right, I have some plots showing this over time. The color code changed going from left to right here, so I'll alert you of that. The bottom part with the brown is coal. And we see that coal, for the most part, was at least 50% of our supply for a long, long time, up until, past 2000, around 2000, it started becoming less and dropping off precipitously since maybe 2009. And then it's been replaced by a number of things. The blue spot here is natural gas, which is a technology we've really grown to replace coal, and largely because of economics. And then we have nuclear power in the sort of reddish, and then renewables on top. So these are the ones I'm going to make distinctions between. We're focusing a lot on renewables, which have grown a lot in recent years. On the bottom plot is the change in renewables. The blue is hydro. Hydro hasn't changed a ton. There's some geothermal related. But the big things that are changing now that we're concerned about is, since 2010 and a little bit before, are wind and solar, because they're very different types of sources. And I'm going to mean that in a dynamic sense from a power grid stability point of view than just traditional. It's not that they're not fossil fuels and things like that. There's more to them than that, and I'll talk about that. Wind has gone up a lot, and then most recently, a lot of solar has come up. So what does this have to do with power system dynamics and stability and those oscillations I was showing you on the first page? The thing is, they connect to the grid in different ways. So I would say natural gas, coal, and nuclear and hydropower connect to the grid in a very direct way. There's some mechanical force or energy that's driving a generator or an alternator, if it were your car, the electrical device that makes electrical energy, or converts it for mechanical energy. So on the left-hand side, we have something turning a shaft literally, and there's a device that has a rotating magnet in it that creates electricity on the output. And we connect this directly to the grid. There's no buffering. It just directly, wires are connected to a grid of wires. Different wind and solar are very different from this. Not only are they renewable and don't have fossil fuels involved, they connect to the grid in a very different way. So on a wind power plant or wind turbine, there is something mechanical turning the turbine. It's the wind that's turning it, but it doesn't connect directly to the grid. It will connect through some power electronic devices and some fancy circuitry. So it's buffered from the grid, and the grid is buffered from it, was one way you could put it. But it makes a big difference because it decouples it from the grid in some important ways that could impact stability. And that's what I want to talk about. And solar is completely different to begin with. It doesn't have a mechanical input. It has solar cells, so it has a DC electricity output that also has power electronics to convert it to AC because our grid runs on alternating current. So it's also buffered from the grid through power electronics. And we call these inverter-based resources because that's the technology we call the specific type of power electronics we talk about when we're having the energy going from one side to the other and we're connecting on the grid side. It's an inverter. So inverter-based resources, what we will refer to these as. And they are important in the distinction of how they connect to the grid. So how is the grid controlled and why do these inverter-based resources matter? Well, I'm going to back up a bit and talk about jurisdictional issues first. The responsibility for the reliability of the electric power grid goes to the Federal Energy Regulatory Commission, and it's from the 2005 Energy Policy Act of 2005, gave FERC the responsibility for maintaining reliability of the electric grid. They outsourced that to NERC, North American Electric Reliability Council, as they were formerly known. Now they're just NERC. And what they have done is divide up the country into these colored regions here. And within those regions, each entity is responsible for balancing power. So they are called balancing authorities. And how they do that depends on each balancing authority. They might have, these big ones might have sub areas that they internally do some energy balancing on. But these are the responsibilities, these jurisdictional responsibilities. It's clear to note that these don't go along electric lines. If I were to divide up a graph or a plot of the United States and come up with electrical regions, you wouldn't come up with this particular plot. This has Chicago separated from PJM here, but Chicago is jurisdictionally part of PJM, Pennsylvania, New Jersey, Maryland. But it's not electrically look like that makes any sense. The Midwest, not Midwest ISO anymore, Mid-Continent ISO, going from Canada down to New Orleans. And it has a very thin connection here. It is actually connected. Really thin connection here from north to south is not what you would design as an electrical system. It's a jurisdictional thing. Oops, I went backwards, sorry. Anyway, I don't want to dwell on that too much. I've already dwelled on it too much. But these are where the responsibilities are for balancing power and entities. So FERC has ultimate responsibility through the Energy Policy Act. They've hired NERC to do this, and NERC does this, and they divide up into regions, and each one of these regions has authority and responsibility to maintain reliabilities in these areas. So how they do it? Well, there's a lot of balancing of power. So generation, power and load must balance because energy goes in the system, it has to come out somewhere. And so this happens in real time. So if the load, end use loads, like all our computers and everything else going on, exceeds the generation, then the frequency of the system will drop. And the frequency is tied to those rotating generators that I mentioned before with these turbines and the like. If the generation exceeds loads, the frequency rises. And we don't want these things to happen. We want to be able to control the system. We don't like it to be uncontrolled. So we balance power to make sure that works. There is energy storage in the system, which can be used either as supply or load and can be used to help out with the energy balance. And in some places like California, they have a fair amount of utility scale energy storage that is exactly used for this purpose. So when it needs to be a supply energy and it's charged up, it does so. And then when we can use it as a load to recharge, we do that. But anyway, that's an overall goal, balancing power, balancing energy. The grid operates on that principle. These inverter-based resources and impact, in particular these renewable generation types, challenge this power balance in a number of ways. One, they aren't controlled to actually aid the power balance. It's not in their agenda. They could, and sometimes could be used for this purpose, but don't. It's not really what they're there for. They often increase the need for reserves and controls, and I will mention this more, even though it's not the focus of this particular talk. And sorry, they reduce available controls to stabilize the grid. So if we take a controlled resource like a coal plant, because we do want to replace coal plants with renewable generation, we want to have a sustainable grid. That's the type of thing we want to do. But one of the advantages from a stability point of view is you can dial up a coal station, have its power go, completely control its output on power. Same with natural gas. Nuclear, we tend not to want to move around much, but we could. And hydro is a bit different in that there's a lot going on with hydro. There's dams built to control water. So it's not there to just supply electricity. It's there to manage water and water resources and water rights. So we don't really want to move that around too much either. So, but it's things like natural gas where we really want to be able to control the system. And we lose that control when we have these other type of resources come on. It also, in some instances, make it harder for grid planners to anticipate problems because a lot of the solar in the distribution network, say, and other resources, IBRs that are smaller scale, grid planners just have to make a guess at what's there. They don't know. And so that makes it problematic for doing planning. Actually, in this past year, or was it last year, FERC passed a resolution to change this so that this information will have to be gathered and will have to be shared with grid planners. But it's not happening yet. It's that hasn't come to fruition. So we're still in an area where people just have to guess what's out there, what resources are out there, and don't know. So that's challenging. I want to talk a little bit how the generation and load balance is implemented in practice. So there's a measure, it's called an area control error. So I showed those balancing authorities where NERC divides up the country in balancing authorities. Those previously used to be called control areas. So area control error is a measure of the imbalance in power in these balancing authorities. And I'll have a slide on that in a minute. There's control systems tied to that notice that the system is out of balance. That uses this ACE signature, and it's called automatic generation control. And it sends a signal to generation about every 4 seconds to update their output to try to bring the system into balance again. And then there's reserves that are potential resources, but that aren't being used, but can be used to track load if when it changes and the system potentially goes out of balance. So I have a plot here to try to describe area control error sum. Here I have a traditional setup where we might have, these are going to be, consider them coal plants or natural gas plants. There's city and residential stuff here, maybe a little bit of wind power here. In this balancing authority, we keep track of energy going in and out or power going in and out of this area, our jurisdictional area that we have responsibility for. And we compare the energy flow between our area and outside compared to a schedule, because there is a schedule. We export power, we import power, we buy electricity from somewhere else, we sell electricity somewhere else. So there's a schedule for that. We actually have a market for that. We're scheduling things. And that's what there is. So we have a schedule. What we do is keep track of the error. That's the first part of the equation down here, is this interchange error. The difference between what the schedule is and what actually is happening. And then that will be part of this error, this area control error. If say we have one of these plants, these power plants in our area goes out, then suddenly we're going to be importing power to supply our cities and our residences, because we just lost some of our own generation. So we're going to be importing, but that's not part of the schedule. So that'll become part of the error here. So this is a local measure of error. And then we'll take this error, we'll send a signal to these power plants every 4 seconds saying, we have this error, we need more electricity, generate more, or vice versa. So yeah, so that's how it works. We keep measurements of how our area is doing compared to a schedule, and we adjust based on it. There's also a system level component to it. It's the second part of this equation down here. And how that works is it relies on the grid being stable and synchronized. So the frequency in Madison is the same as the frequency in New York, which is the same as the frequency in Miami. It's all a connected system where the frequencies are, the system is synchronized and we all share the same frequency. There's minor fluctuations, very small millihertz fluctuations are smaller, but in general, it's just going on a continental scale. The frequency is the same, at least in the eastern part. West is separated, Texas is separated, Quebec is separate. Yeah, so we're all synchronized, but what happens when there's an energy imbalance? Well, the frequency will rise or decrease depending if there's more generation or more load. So when we lose our power plant, the frequency is going to go down across the network, and that will cause all other generators to adjust their outputs to try to keep the system stable. And then we'll keep the system stable, and then we'll eventually slowly revert back to the ideal operating point where we'll get the area control error back to normal. We'll reach schedule and the frequency will go back to normal. It's a beautiful system. It's beautiful because it works on local measurements. The frequency is sort of a system-wide measurement, but we can measure it locally, and it keeps the entire grid on a continental scale. It's amazing that we can keep something so big on a continental scale stable. And that's how it works. It keeps track of an imbalance in power and adjusts the electricity for that. This gets challenged with some renewable resources. And in this case, it's not because our IBRs, we'll come back to what that does, because it replaces controllable generation with generation that's not being controlled for this purpose. So of solar, which you may or may not know it's there. We can have industry scale solar as well, and wind, and we're moving the knobs of things we can change. So that's a challenge. That doesn't mean it's a bad thing. We like renewable energy, don't get me wrong, we want this stuff. It's just one of the challenges that comes up. So we need reserves to guard against fluctuations. So we need to reserve energy that we can control to adjust for fluctuations. So here's a wind. This is an old plot, but it's one that really highlights this issue. There's 3 lines on this plot. The blue line is the load in Texas. So this is the end use loads, the cities, neighborhoods, residences, how much they use. This is a 2-week scale, and you can see the daily variations in load. During daylight and at nighttime, you use less energy at night. The small variation one is probably a Sunday, because Sundays, there's less fluctuation in power, but I don't know that for sure. I didn't look up that date. So that the load fluctuates on a daily scale. Wind also fluctuates, and Texas has much more wind than this now, than this is an old plot. But it also fluctuates, and what it does is, from the viewpoint of the controlled energy sources, the fluctuations they have to track are bigger with the wind power than without, because the blue line has these fluctuations. But if you account for tracking the variations due to wind, the green line has substantially, it's probably 50% more fluctuation size than the blue line. And then we need controllable resources to be able to track that. So this is an issue and a challenge. It doesn't mean we shouldn't do this. We do. We want to do this. We just need our engineers to take this into account and make this all work. It's a challenge. It's not the challenge I want to talk about today, because this is an old challenge that people have worried about for a long time. I want to talk about the controls that maintain stability on the second-by-second basis, not on a slower load tracking one. And there's 3 traditional controls that do this. There's the automatic generation control that uses the area control layer, and I talked about that. There's a droop frequency control that's meant to arrest a possible instability when there's frequency is undergoing a change. And then there's power system stabilizers that keep the grid synchronized. So here's a plot. I want to show you all three of those, or all two of those controls in action. This is about 40 seconds of data. The axis on the y-axis is frequency measured at a location in the Western United States. I'm not going to reveal locations of the data I get from for reasons of where I get the data from. They're very careful with data. I don't think it matters here, but in any case, could be almost anywhere in the West. And there was a big disturbance here, a loss of a generator somewhere. And then the frequency dropped, and it dropped from 59, almost 60 hertz to 59.7 or 300 millihertz. That's actually a fair amount of power lost, and it dropped. But in terms of the dynamics and the controllers I want to talk about, you see these fast oscillations that sort of dampen out and die out. Those are oscillations with keeping the grid synchronized, the generators spinning together at the same speed. So this is a synchronization of the generator so that the frequency is the same at all of them. So that's power system stabilizers are the technology we use for that. There's this frequency governor response that uses a local frequency measurement to stop the frequency from dropping. So it arrests this dynamic and brings it off to a level. It uses something called droop control. And what that means is that the steady state frequency drops as a consequence of this control action to stop the instability. So it dropped from 60 hertz to 59.8 hertz. But it's stabled out. The grid is synchronized. We don't have these fluctuations anymore. The frequency is stable. It stopped. It's not at 60 hertz, but it's stable. So that's a stabilizing controller. And then there's slower controllers that I was talking about using the ACE, the area control layer, and automatic generation control, that over minutes will bring this frequency back up to 60 hertz or whatever the scheduled frequency is. So these are the three types of controllers we have. Today, I'm going to worry mostly about the synchronization part of this. We want to keep the grid synchronized. That first plot, which we'll see again on the first slide, which had the instability that I think is so cool, is an example of the grid losing synchronism. So this is the stability part that I'm interested in talking a little bit more about today.
Hey, Bernie, we do have a question from the audience here.
Sure.
Kermit asked, why is wind-based power operated as IBR? And he says, I understand solar panels generate DC that needs to be converted to AC, but I thought wind turbines drive rotary generators, which typically produces AC.
It does, but and old wind turbines were operated that way, and they were just directly connected to the grid, but they aren't anymore, and they haven't been for a while. And the reason you might want to not do it that way and have power electronics in between, the wind comes in at different speeds and will want to turn the generator at different speeds, and you want to let it do that. But the grid is at 60 hertz. So if you had an old type of wind turbine, you would have a synchronous generator on a pole with some turbines on it, and it would be synchronized with the grid, and it would have all the same characteristics I've been talking about with grid synchronization. But that's not how they're operated anymore. They are different types of generators that will spin at different frequencies and not be connected to the grid 60 hertz. They're connected through some power electronics. The power electronics are the inverters. And so this would be considered an inverter-based resource when it's connected to the grid through power electronics. And most of the wind turbines are done this way now. Almost all of them would be done this way and have been for a while. So they are buffered. The distinction is they are buffered from the grid dynamics through power electronics. The old ones were directly connected, but that's not how we're doing it anymore. Okay, so I wanted to explain where these electromechanical oscillations come from. So sorry about the equations. I'm going to have a few equations. They don't really have any purpose except to remind you if you've seen this before. If you haven't seen this before, I wouldn't worry about it. But it's a reminder if you've seen rotational dynamics of things where you have torques and masses spinning. That's what happens inside a generator. We have mechanical power turning an electromagnet inside a generator that induces a power in electricity and makes electricity. And the mechanical part looks like Newton's laws. If you remember Newton's laws for rotational dynamics, you have a torque coming in, which makes the thing want to spin. The spinning makes its angle, so theta would be an angle increase. And then balancing this out is an electrical torque that's related to the power going out of this generator. So when they're in power and balance, this is zero, we spin at a constant speed, whatever. You either have seen this before, you most likely, you're all educated people, have had physics before, so you probably have seen this before. But it is because those generators are rotating equipment, they have rotational dynamics. What we have here is a network of these connected. And when they're not inverter-based resources, when there's no buffer, they're literally connected by wires. They're just one generator is connected to another by wires, just directly connect. Well, there's transformers in between. So electric wires to transformers to more wires, but there's just an electrical conduit just directly connecting all the generators together. They're just generally just connected right together. And some people try to make a mechanical analogy to springs. If these were all springs that were connected and you wiggled one, then it would ripple through and wiggle the rest of the grid. That's what happens here. When there's a mechanical wiggle in one of the generators, it is electrically coupled to all the other generators, which induces a mechanical wiggle too. So without any power electronic buffers, these things are just directly connected to each other. And on a continental scale, so this is a plot I made out of EIA data, they have a mapping system. This shows the coal plants, natural gas plants, and nuclear plants in the country. These are the ones that, are controlled in this way and have this technology. So they're all over the place. So if one wiggles, then it'll make the ones around it wiggle, and we'll get these oscillations spreading throughout the grid. So that's how it works. Those mathematically inclined could take up all the dynamics of all the generators, combine them in big matrix form. And if, again, this is just reminding the experts who've done this before, they've seen it before, that the structure of this matrix with the zeros on the diagonals and the non-zeros on the off diagonal tend to lead to oscillatory dynamics, things that oscillate. And without anything on the diagonals, these tend to be very poorly damped. They oscillate a lot. So this is why power systems have oscillations, because we have a bunch of generators who look like Newton's electromechanical dynamics, all linked directly through electric lines. And we really see these oscillations. So this is actually a slide I took from somebody else's presentation, John Undrell and Dmitry Kosterev. They made to a NASP presentation a long time ago, but it explains this and shows this idea. On this plot down here is frequency measured at different locations as a function of time, and there's 25 seconds here. Sorry, 30 seconds here. And the blue line is in the north part of this system. It's actually at Grand Coulee. It's the largest plant in the United States. It's a hydro plant. It's eastern Washington up near Canada. It's a big power plant. Sorry. The red line is down in the south. It's near LA. It's Devers. It's a substation near Los Angeles. And you see they're totally out of phase. When the blue one's going up, the red one's going down. And what this is indicating is that the frequency is increasing in the north, the frequency is decreasing in the south, and vice versa. So the generators in the north, when they're speeding up, the generators in the south are slowing down. And so then they reverse themselves and they oscillate. And that means that there's energy flowing from north to south and south to north, and they oscillate. And we see these. The purpose of this slide is to show you that we actually see this phenomena in the grid. This is very poorly damped. We're very, very lucky this did not have a blackout. This is not a operating condition you want to have. Exactly not. Okay, so these oscillations that are going from north to south, I've shown you here between Grand Coulee and Devers, is usually occurs around 1/4 hertz, and that's about what this one is in this plot, and has a name. It's the north-south mode. There's actually a couple north-south modes, but this is a main north-south mode. There's other ones we know about. Alberta is weakly connected to the rest of the grid. Sometimes it's not. It just trips off by itself. It has a frequency where it'll show similar oscillations of Alberta to everywhere else in the grid at about 0.5 hertz. There's another about 0.5 hertz in the south that's between Arizona and California, or the rest of the grid. And there's a power plant, a big power plant coal strip that's in Wyoming, a big coal plant that connects very weakly to the rest of the grid. So when there's a disturbance, it wobbles at about 0.7 hertz. So it will go up while the rest of the grid goes down, and vice versa at about 0.7 hertz. Yeah, so these things really do happen. So our interests in this, real-time situational awareness, one of our interests is vulnerability. So I'll get back to percent damping in a second, but we don't want to wait till we see these wiggles to do anything. We want to know we're vulnerable to such things before then. So we'd want to look at this ambient data before the disturbance and say, oh, 3% damping, that's not very good. Let's do something about it. Because when something happens, the characteristics of the system will change. So when we have a disturbance, we can be optimistic and say the disturbance will be beneficial and actually make the system better and well damped, but I wouldn't count on it. When we had this disturbance, it made the system worse. And so the damping got worse and actually became unstable, and it blew up and we had a outage. Again, this is decades old, but it took out the western part of the country. It's a beautiful plot. I love this plot. Yeah, but we want to get to doing something before this happens. What I'm going to talk about more today is examining changes in damping over time. Are IBRs really reducing damping and decreasing stability margins? Because this is something that engineers talk about. With these new devices that aren't directly connected to the grid, aren't controlled to help out, do they make things worse or no? Let me see. I guess worse is okay word. I should say challenging though, because engineers like challenges and will make the system work. But we got to address these challenges. Are they creating a situation where we have to address some challenges? And then we're going to look at data, so there might be other stuff we see in the data. So percent damping is a term that engineers use to talk about how well the oscillations we see in the grid, how well they decrease over time. So here I have a plot of an oscillation, and I think most of you are engineers. You might know what a time constant is. So I have a plot up here of an e to the sigma t. Sigma is usually a negative number. That part is the envelope of this waveform, the dotted line on top. It creates an envelope. Then it's multiplied by a cosine, which is just the oscillatory part of this. So it bounces up and down, the oscillatory part. And the time constant is a measure of this envelope, how fast it decays. The time constant you can graphically compute by taking the tangent line of the envelope at the start, project it down to 0, and the amount of time that takes is the time constant. And that's the time constant. So if this envelope took longer to decay, the time constant would get longer. If it decayed faster, the time constant would get shorter. So when we say percent damping, I have the equations over here for it, but one of the interpretations for it is it's inversely proportional to the number of cycles you'd get per time constant. So in this case, 3% damping corresponds to about 5.3 cycles per time constant in time. And so the takeaway, what you really want to know is that low numbers mean low damping, and that's bad. So when we say 3% damping, that's not a good amount of damping. A high number, like 10 or 15% damping, that's good. So we'll have higher numbers better. It means that these oscillations go away faster for high damping. So that's a term I'll use, and that's a term people use. So we want to look at data. And in fact, what we have is phasor measurement unit data. It's time synchronized, GPS synchronized data from around the grid. the data I generally have access is in the western part of the United States because my historic ties there. So what we want to do is look at data like this. This is voltage data. And look at features. There's a voltage dip during the disturbance. If it comes back, there's a final voltage. And then there may or may not be oscillations. When there are oscillations, we want to know the frequency and the damping of the oscillations to talk about stability. In fact, I want to focus on the damping. And we may be interested in the magnitude and phase of those as well, although the voltage dip and the final voltage will say something about that by itself. So how do we take data and calculate the frequency and damping of oscillations? Well, industry practices uses Prony analysis in similar systems that are based on auto-regressive techniques. And yeah, well, I have a special slide on that in a second. So estimating oscillation frequency and damping, there's two different ways of really getting at that. One is if you have these obvious cases where you see the oscillations, you can fit the data to a linear dynamic model. That's an auto-regressive model, AR model. Most of you, this isn't necessarily an engineering thing. This is used everywhere, auto-regressive models for fitting time series data. It's the most common thing to do with fitting time series data. So chances are you've seen this word before, but maybe you haven't. Anyway, you fit a dynamic model, and then you determine the natural characteristics of that model. You do the models, you say, well, I have this model. What type of frequencies would we expect it to see naturally come out, or how well damped would be those? So you just compute the characteristics of the model. Yeah, so that's what we want to do. That's the most common way. Another way is if you can see the oscillations, just use curve fitting. Directly fit the observed response to some decaying oscillatory exponential, and just compute it directly. So there's advantages and disadvantages for either. The Prony one, the one that uses an auto-regressive one, the one is years old. It came about in over 200 years ago, 1795. Prony was around. And you construct, this slide just says exactly what I was just saying. You construct a linear model, you compute the natural modes of the system. Those are the frequency and damping of oscillations. You could fit the model. The third step isn't necessary for what we're talking about today. We just want to know the natural modes. This is easy. The math is easy. It's a linear calculation. It's almost trivial to do. So it is a very popular approach. My experience with these Prony-like methods, the ones that develop a linear system model and then calculate the characteristics models, they're really finicky. They often require methods for pre-processing the data, even throwing out data, just downsampling, because too much data messes this system up. And that's kind of mind-boggling, but it's true. Often require a large number of assumed dynamics. Even when it looks like you have a simple response, you have to fit it to, or even overfit it to a different type of response to make it work. And it tends to be sensitive to relatively minor changes in data. And this is not something you want in a tool. There's variations on it that work better. I would never just do the 200-year-old Prony. I don't recommend that at all. But there are some variants on it that are more robust. So a matrix pencil method, which I'm not going to go into here, it's more robust and works reasonably well. But it's one option. Another option is just so the benefit of that approach was it's easy and fast and mathematically simple. You can also do curve fitting, where I'm going to assume that I want to take the data I have and fit it to a curve. Here you see our cosine, our decaying of cosines here. We'll throw in a magnitude and a phase, but it has a damping coefficient and frequency. And maybe there's some other dynamics we want. And we just do a curve fitting. We minimize the difference between our model and the measurements we have. And we could do that. We can pose the problem, but it looks rather complicated. It's nonlinear optimization problem, minimization problem, least squares problem with transcendental functions, cosine trigonometric functions. So it's not it looks complicated. Well, here's the thing, and it's the conclusions in the middle. It is complicated, but it's a solved problem. It was solved in 1973 by these professors at Stanford. It is complicated. The purposes of this slide is not to actually teach you any of these equations. It's just to show you that these equations are complicated, and it is a complicated thing to solve, but it's not 200 years old. It was solved 50 years ago. So there are ways to do this, and using variable projection techniques, and they're out there. So we can do this. We can do this sophisticated curve fitting. Back when I first learned about it, I went through all these equations and learned how it actually worked, but that was years ago. I actually have to review it to actually. Don't ask me any questions about this slide. I couldn't answer them at this point. There's additional benefits to this curve fitting approach, is you can take multiple signals and combine them to say something interesting. And you can do automatic detrending of signals if you have linear stuff in that. Okay, enough of that. Back to our current interest, we want to get something out of ambient data, not the wiggles. And I was just talking about fitting things to things that look like decaying exponentials. We don't have that over here on the left. So I want to constructively show you how we do that. On the plot here on the left are frequency measurements, a half hour's worth of frequency measurements, one in the north part of the western part of the system, and one in the south location. And again, I'm not supposed to share data, so I'm not going to identify where these are. I will tell you they're not Grand Coulee and not Devers, not the ones that I used for the previous slide, or I showed you somebody else used for the previous slide, because I don't want to reveal anything. I don't think it matters if I would, but just to be fair with the people who provide this data. So you can see the frequencies, the system really is synchronized on, for the most part, these things move together pretty well. There are slight differences, and that's what we're going to exploit. So we subtract one signal from the other, the frequency measurement, the y-axis is frequency here, and this is a half hour's worth of data. And we get the thing on the right. When we subtract one from the other, we remove the common mode. And I've actually chosen these locations to accentuate the interesting modes that we're after, the interesting oscillations are after. But it still looks like noise. So how do we do curve fitting to fit to this? Well, we do a standard technique for analyzing noise and trying to reveal information in noise. And that's to take the autocorrelation of the signal. And the autocorrelation is over here on the left. It's just a statistical type of calculation. It's not quite right. I'm going to do a poor description of it. But in any case, you can calculate an autocorrelation that does reveal some of the dynamics underlying the system. And in this case, it's showing us this decayed exponential. And if you look closely, and you probably can see because we're doing this online over Zoom, there's these wiggles, these high frequency wiggles on there. And those are sustained. They don't actually go away. So when we try to fit this to a decaying exponential, we get an exponential that's about 1/4 hertz, 0.24 hertz, and it's about 13% damped. So that's actually pretty good. So that's not bad at all. That's a damping. And then there's these undamped things that are happening, and I don't quite know what they are and haven't had a chance to look. If we look at the spectrum of this noisy data, we'll see this is a spectrum, so it's frequency and frequency content on the y-axis. You can see a bunch of stuff mostly at the 1/4 hertz. That's the dominant behavior of this, and that is the dominant behavior on the left. But there are these things happening at very discrete frequencies that look like pure oscillations. And that's these wiggles that we see, the high frequency wiggles here. Not important for what I'm talking about today, but they do exist in this data, and they're not just not bad data. Okay, so I'm going to speed this up. I'm running out of time. So we wanted to do a study where we try to see if the frequency and damping change over time. So what we did is want to collect data from different years at about the same conditions. And weather is the most impactful thing about conditions for a power grid. So what we set out to do was to say, on September 1st of each year, plus or minus 2 weeks, find days from each year that look very similar from a weather point of view, and go back about 10 years. Turns out we only have access to 7 years worth of data, so we go back 7 years for this. So we're getting data from the West. So we're gonna look at Seattle, Portland, San Francisco, Los Angeles, and Phoenix, and try to look at the average temperature, low temperature and precipitation, and try to come up with one day each year in that time frame so they look good. So there's a lot of challenges. There's a lot of combinations to look at, and the weather what does it mean for the weather profiles to be close? So we looked at two different ways of doing it, minimizing the mean difference between the profiles. It could be average temperature and whatever, from each of the days from each year. And then we also did a geometric mean distance. I'll just say up front, the mean difference seems to be the way it's going to look best for us. So how do we do this? How do we find days that look the same? Well, because there's so many combinations, the first thing we did was use a clustering algorithm. And we just stacked up all the weather data from the days we have and grouped them together to ones that look similar. And then we increased the number of clusters because the smaller number of clusters you have within the clusters, the data from those days look even more similar. And then we increased the number of clusters until there weren't any more that include one day from each year. So we stopped when we had clusters, small clusters, which had at least one that had one day from each year. And then we picked the best combination from those days. A second approach that we looked at was just brute force. It turns out if you have 20 days per year, looking only at weekdays for over 2 weeks plus or minus of September 1st, you get 20 to the 7th combination, which is 1 billion combinations. That's a big number, but computers are fast. So we could use brute force and just look at all 1 billion combinations. And we did, or at least the student, Yvonne, who's working with me, did this, wrote some MATLAB code to do this, and it takes a couple hours to run. And so that's probably the best way to do it instead of doing we don't need to do the clustering. We can do the brute force for 7 years worth of data. So this is a sample using the best mean distance. The day representation is each column, one day each year. And so that's the sample. And then we'd calculate a distance between 2 points by putting this in a 10-dimensional space and just calculating the distance. I'll give you about 30 seconds to look across to see that whether these are reasonably similar days across the years. Going from 76 degrees, 73, 78, 77, 81, 77, 78, they look reasonable. The high is in Phoenix, 105, 105, 102, 105, 105, 102, 109. They're all hot days in Phoenix. So San Francisco, the high 66, 70, around upper 60s, low 70s. To my eye, these look like they're very similar days. So we're going to want to calculate the damping and frequency at each one of these days and compare them to see if it's been changing over time as the grid has changed. So we did take these days. We reached out to our colleagues in the West, and they sent us days worth of data that we could study. Where we really are now is just cleaning up this data, because there's bad data drops where all the data disappears at some point in time because there's just some communication error. There's obvious bad data where the system just didn't take a good measurement, and they either listed as not a number or they listed as 0, and you can easily identify those bad data points. There's strange odd data points where it reports the frequency 63 hertz for a data point or two. The frequency is never 63 hertz. So there's strange stuff. So this is where we really are. But I wanted to present something today. So I grabbed a half hour's worth of data from 2018 and a half hour worth of data from 2024, almost exactly 7 years apart, and did this analysis on that 1/2 hour worth of data and computed this using the ambient data, the frequency and damping of oscillations. So in 2018, it seemed like this is what I showed you earlier, 20.24 hertz, 13% damping. The computations I got for 2024 was 26 hertz, 0.26 hertz, and 11% damping. So this seems like the frequency of these two samples It increased in 2024, and the damping went down slightly. Now, the frequency you can see, literally see from this plot. If you look at the second peak, it occurs earlier in 2024, the second peak than in 2018. The frequency of oscillation is clearly changed a little bit between these two samples. It's harder to see whether the damping is decreased. I guess if you look at the second part of here, like the second swing of this, it does look like it's swinging a bit more in the bottom sample. So it looks like the damping looks a little bit less. It hasn't decreased as much in the bottom thing. This is where we are. We're trying to look at one of the major things that has changed in the grid has been changed with reducing the number of controllable resources we have, reducing the amount of inertia, physical inertia in the grid as we retire coal plants and if we were to retire natural gas plants, both of which we might expect, the hypothesis is that we might expect them to both increase the frequency of oscillation and decrease the damping. 1/2 hour sample from this data is not enough to be conclusive. We haven't, I would have hoped to have been further along today, but wanted to show you something. There's a second aspect that we hadn't talked about is large loads are like IBRs as well. They have a power electronics connecting them to the grid, and they reject grid disturbances. So they react differently than some of our traditional loads like large motors and the like, which will have some dynamics that integrate with the grid. So there could be a secondary effect, especially when we have very large loads that might be influencing this behavior as well. And so we might look at that some more as well. I'm sorry I only left myself 5 minutes for questions, but let me open it up for questions.
Yeah, thanks, Bernie. Yeah, we got a couple of questions. So first is a follow-up to the earlier question about why was the wind turbines changed from the traditional kind of inertia based to the inverter based resources, and then overall, if you can expand on what you just said about how do the IBR generation systems make controlling the grid imbalance and system oscillations more challenging, and how significant or expensive to address are those challenges?
Well, they may not. That's the hypothesis of this whole work, is to look at data. People talk like they could be detrimental to the grid, but we don't know that. So that's the purpose of this study, is to look over years worth of data to even see if the grid looks less stable than it used to be. So that is the purpose of this study. Why they might react that way is we're reducing the physical inertia, rotating inertia that's connected to the grid directly by introducing these power electronic buffers. So if we retire a coal plant, there's a big mass, rotating mass that's no longer on the system that provides energy to try to maintain frequency during a disturbance. So that's the notion of why potentially could have a detrimental effect. It doesn't mean it does. That's one of the purposes of this study, is to show whether changes in the grid over the last 7 years really is showing any difference. And then there's a second question. Even if there was changes, we still might be a stretch to actually say it's due to these retirements of inertia or anything else or lack of controls. It's a hypothesis that people have put out there. Why have wind power plants changed from being directly connected, where their inertia is immediately available to the grid and business to the grid, and being power electronic buffered? They operate more efficiently this way because you can operate the wind turbines at variable speed, and the wind is putting a different force and wants to drive them at variable speeds because the wind changes and it will want to turn the thing at a different speed. So you can make use of that. You have an AC output you absolutely do have an AC output of the wind turbine internally. It's not 60 hertz. It's whatever it is, and it can go over a wide range. The power electronics will just convert whatever frequency is at to 60 hertz so you can connect to the grid. And it just makes it more efficient, more energy efficient to run it that way, where you can operate the the wind turbines at variable frequency, you can get more of your energy through on average if it's not connected directly. So it's entirely economics that drives that technology. It makes it more efficient to do it that way, but it does buffer it from the grid. That inertia that's in the wind turbine is no longer seen directly from the grid. The energy goes to inside an inverter, will go into a local DC storage. You could think of it as a battery. It might be a big capacitor, whatever it is. And then through an inverter, converted back to 60 hertz.
Great, thanks. And then one more question we've got, what do you see as the role of battery storage in helping with this issue as well?
Battery storage is very helpful because it's another control energy that can be modulated. It's not generally used for the synchronization that I've shown here. It is used for these fast trends, like when I was talking about those bigger fluctuations that are seen by controllable loads or controllable supplies because of the wind power, or with the very fast ramp up and when solar turns on in California, because they have a ton. You see these enormous ramps in energy when it turns on, so the storage can store that energy during that time. And when the sun goes down, it can supply the energy. So batteries are being used for that purpose now, for managing the load. They aren't being used right now for the synchronization issue, stability issue that I'm talking about yet. And that's fine. Maybe they're not needed for that purpose yet, but they could be. And so that is something that down the road, if the synchronization stability issue really becomes a problem, then they very well might be used for that purpose. Yeah, I see a role in them, absolutely, for them. And they would be a really good application for them, because this type of synchronization isn't needed for very long. It's like 30 seconds or something. We just need to keep the grid synchronized while the other controls come up. Where was that plot I had? One of them, the bad plot. Here, this plot looks like normal controls. If you smooth out the variations here, this looked like what the grid should be doing. It arrests the change in this case, it's not pretended frequency, it's not frequency. It arrests the dynamic change, and it would level and flatten out like you would want it to for stability thing. But it's losing synchronism. So these big plots are not the slow controls that are working well. It's the synchronization controls that aren't working. So I could see battery storage helping them. It'd be ideal for battery storage because it's not needed for long periods of time. Yeah.
Great. Well, I think we're out of time, and looks like we've addressed the questions. So thank you so much for your presentation and sharing your insights today, and good luck, completing and learning more insights from your research going forward.
All right. Thank you. And thank you all.
Thanks. And we hope to see you all back in 2 weeks for our next Sustainable Energy Seminar. Have a good day.